In this lecture, we are going to study about the Fermi level and the Fermi energy. Fermi energy. So here, we're going to talk about the Fermi-Dirac distribution law. So the Fermi-Dirac distribution law we had written down is nothing but Ni Ni is equal to the power of alpha plus beta I plus 1. So plus 1. Okay. So this was our law. So now we're going to again talk about a continuous distribution. So I'll change it to a function of n as a function of e. So g also will become a function of e, and this will also become a function of e. Now the Fermi level is the Fermi level is that energy. So we call this energy. We call this energy. The energy is equal to the energy of E. Oh. So it's that level of energy that all the states are completely filled. Okay, so all the states are completely filled at T is equal to 0 Kelvin. So if all the states are completely filled, then what we call as the occupation index will be equal to 1. Okay, because this is the number of electrons with this energy. This is the density of states at this energy. Okay, so each particle can and occupy only one single state density, one single state with this energy. Okay, so so therefore uh, this value can vary between 1 to 0. 1 means all the states in that energy, each cell is completely filled. Okay, and if it is 0, then it is completely unfilled. So this at this temperature is equal to 0 Kelvin, the energy value at which all the cells are completely filled, each state, right? So the density of states in that particular energy level, there are so many states. If all the states are occupied by one let's take the electron. Okay, so we are talking about the electron. So if they're occupied by one electron, then it refers to this value refers to 1. Okay, so this value refers to 1. So this is when E is equal to EFO. Now when at this condition we can derive that the value of alpha, when you substitute this condition here, we can derive that the value of alpha should be equal to, so the value of alpha should be equal to minus EF by EF is the Fermi energy KT. Okay, and energy also, of course, here energy also should be equal to the Fermi energy. So if you substitute that here, what you see that the denominator will denominator will become e to the power of minus infinity. Okay, so this denominator will become e to the power of minus infinity. So let me write it out here. So you'll see it more clearly if I write it out this way. So this will actually be E by KT, right? So this will actually be EF by KT then, and alpha is nothing but minus EF by KT, which will make it e to the power of minus infinity. Okay, so they'll make it e to the power of minus infinity. So this EF can actually be, E itself, but the condition should be that E should be less than or equal to EF. So it should be less than or equal to EF. So that is the condition. Okay. So now Notice that t is equal to 0, therefore this entire term will become infinity. Okay, so this entire term will become infinity. Okay, and therefore you will get the this condition, you will get back. So you will get back this condition. So e to the power of minus infinity then. So e to the power of minus infinity is nothing but you have 0. Okay, so e to the power of minus infinity is 0. So this term will become 0. So you have n of e is equal to g of e, or otherwise you can say n of g by e is equal to 1. So this is our was the condition. So we derived that alpha is equal to minus ef by kt. So this is the Fermi level. So for Fermi level at at an energy at Fermi level, alpha is equal to minus ef by kt. So now let us derive the energy of the electrons in a metal at this Fermi level. Okay, at this Fermi level. So we'll call this energy the EFO, the EFO of a for electrons in a metal. So for electrons in a metal. So this particular distribution function is useful in the case of studying electrons in a metal, because the electrons in a metal behave like a Fermi gas, because they are we have the metallic bonds, right? The nucleuses are uh, you have the nucleus is a solid course, and the free electrons are freely moving about between each one nucleus to the other. So it can behave like a Fermi gas. Okay, so therefore this distribution function is very important to studying this kind of phenomena. So we'll derive the EFO for electrons in a metal. So therefore n is equal to, so we had written down the in terms of the continuous distribution, Ne dE so the total number of electrons, first we'll derive the number of electrons and then we find the energy of the electrons. So the total number of electrons will be the integration of the number of electrons in a small energy interval dE integrated from 0 to EFO. That is the energy level, right? That is the Fermi energy level where the occupation index is 1. Okay, so the occupation index is 1. So where the occupation index is 1, we know by this condition where E, the energy is less than or equal to EFO, the occupation index. Okay, so we've said that the occupation index is 1. So let me call this out. So this is called NE by GE. This is called the occupation index F of E. So this occupation index is 1, and we have the temperature is 0 Kelvin at this point. So I can might as well write by this condition Ne is nothing but equal to Ge at this condition. So therefore this integral is nothing but now n is equal to 0 to EFO G of E integrated with respect to B. Now, of course, now I have to derive the density of states. So that is our next step, to derive the density of states. Now, this is how we will proceed to derive the density of states. So this is how we'll proceed with the derivation of the density of states. So what we'll do is the phase space volume. So we'd already introduced the concept about the phase space. So we have Q, the position coordinate, the generalized position coordinate, and P, the momentum coordinate. Likewise, this can be therefore this is Qx, Px, and we have Qy, Py, and we have Qz, Pz. Okay, so the entirety of the volume of the phase space phase space is nothing but the integral of, so you have 6 integrals. Okay, so you have basically 6 integrals of dpx, dpy, dpz, dqx. So this concept is because to denote a particular particle, you need a position and its momentum. Okay, so that is why we have this. So denote a point in phase space, you need its position and momentum. So now what we'll do is, let me erase this out. So the volume of the dqx, dqy, dqz is nothing but the space volume. Okay, so the space volume, so it is nothing but saying dx, dai, dz. So this is nothing but dv, the volume. So if you integrate this, you will get the total volume. So I will just write out for the first, this case, I'll erase this and I'll write it as the total volume. I'll remove the integrals, the 3 integrals I'll remove them. Now dpx, dpy, dqz. So this is the momentum space. So in the momentum space, now we'll find the volume of the momentum space. Now we'll take the volume of a sphere. So we'll take a we'll take a sphere and we'll take the momentum coordinates px, py, and py and pz. Okay, so pz, the z component, and we'll take a sphere. Okay, we'll take a sphere. So the volume of a sphere is nothing but 4 by 3 pi r cube. So r cube here will be nothing but p cube, where p is nothing but, rather, p square is nothing but p square is nothing but px square, py square, and pz square. So instead of putting r, I put p here. The radius here, the radius of this momentum space sphere is obviously p. So this is, p is nothing but p square is nothing but, so we have px square, py square, pz square. So now we will substitute for this quantity and I'll write the the volume of the phase space is nothing but v into, and notice p is also, momentum and energy are also related this way. Energy is equal to p square by 2m. So therefore p is equal to, p square is equal to 2me. Okay, so this is one important relationship we have to know. So when you do that, you can substitute as well in terms of E itself here. You can substitute as 4, E is equal to 4 pi by 3 into 2me to the power of 3 divided by 2. Okay, so the power of 3 comes from here and the square root comes from here. Okay, and the square root comes from here. So based on these 3 equations, so the power of 3 comes from here, and based on this equation and this equation, I've written out as 2me, p square is equal to 2me, and based on this equation, we have to put the square root 1 by 2 power. So now this is the volume, total volume of the phase space. Okay, so the total volume of the phase space. Now, how do we find from here the number of cells? So this is the total volume. Okay, so this is the total volume. This is the total volume. And we have to find the number of cells. So the number of cells will give us the number of microstates in the small energy level. So we have to divide the total volume to get the number of cells. So we slowly go from one point to another. So to get the number of cells, we have to divide the total volume. We have to divide the total volume by the volume of each single cell. So the volume of each single cell. So let me erase all the other things that we had used to derive the previous ones. So erase to make some space. The volume of one single cell in phase space. So dpx and dqx. So this is one phase space set of phase space coordinates. This is nothing but h. Okay, so phase space is quantized as h, where h is Planck constant. So therefore, the total volume will be h cube. Okay, so the total volume of one cell in phase space. So volume of one cell in phase space. So the volume of one cell in phase space will be h cube. Okay, because for one set of coordinates x we have h, we have y, and we have z. So this will be h cube. So therefore, the volume of one cell is nothing but h cube. So it is this answer that we got divided by h cube. Okay, so the number of cells. So we call this number of cells as phi of E. So phi of E, the physical meaning is nothing but the number of states. Okay, so the number of states, the number of microstates in the energy level in that particular energy level. So for a single particle, the number of accessible microstates will be equal to the number of cells in phase space. Okay, so this quantity denotes the number of microstates in the energy level 0 to E. Okay, so this quantity that we are going to write out here, 4 pi B 3 H cube 2 M E power 3 by 2. So this quantity here denotes for us the number of microstates, or the number of states in the energy range 0 to E. Now I want, for our density of states derivation, I want G of E. Now G of E is the number of states in that particular energy interval dE. Okay, so that is what I want. So how do I get from here to there? So what I do is, to get that density of states G of E, I differentiate. Okay, so to get the density of states, let me write it out this way. So to get the density of states, I differentiate this phi function, which is the number of microstates in the energy level 0 to E with respect to E. So I differentiate this and multiply it by the differential or differential E. Okay, so this will give me my density of states. So this will give me my density of states. So this is nothing but the G of E dE. Sorry about that. Okay. So when you differentiate this quantity, so you're differentiating this quantity with respect to E. So that will give you 3 by 2, 4 pi. Okay, so let me write out the answer. You can check the differentiation. So the answer you'll get is 2 pi B by H cube 2m 3 by 2 e to the power of half d. So when you differentiate this quantity, you get this term. Okay, so when you differentiate this quantity, you get this term. So this gives us the density of states. Okay, now again, this is in our problem, we'll multiply this answer by 2, because there are for we have to, there are two states. Okay, we have a plus spin electron and a minus half, plus half and a minus half spin electron. Okay, so therefore there are two states of for the plus and minus half. There are we multiply the answer that we get here by another 2. Therefore we actually, what answer we get here is, we multiply by 2, so this answer will be 4. Okay, so because there is two states of a electron, plus half and minus half, the two, to denote the two spin states, to incorporate the two spin states in the density of states result, we multiply this answer by 2. So now we can go back to our problem. So we substitute our g of e value. So let me do it in the next slide. So n is equal to integral of 0 to EFO, and we substitute this answer here. So when you substitute this answer, you get 4 pi v 2m by h square 3 by 2. Now all of this is actually a constant, right? A constant in the, it does not depend on e, because the integration is actually with respect to e, so you can pull it out. So you only have to integrate e to the power of half with respect to d. So when you do that, what you get is n is equal to 8 pi v by 3 2m EFO h square 3 by 2. So now this answer I could just rearrange for EFO. This is what we want. So EFO is nothing but h square by 2m 3n 8 pi p 2 by 3. Now if I want to define a quantity like n, which is the total number of electrons per unit volume, then I could change this to, I can write n here. The small n denotes the electron density. So it denotes the total number of electrons per unit volume. So therefore we've got a result for EFO for electrons in a metal.